All right. Good afternoon. You guys enjoying the change in weather?
Yeah,
It's
it's
kind of
not.
crazy, right?
It's not supposed to get above 80 for like 2 weeks.
Wow.
Or yeah.
Well, I mean, that's in a way that's nice, right?
Oh no, it's
Kind
very
of.
nice. Kidding me?
No, I spent 2 years in Michigan, and I was happy to come back south because I grew up in Georgia, and then Michigan was a different animal. It was like as soon as August was like halfway through, then you're not hitting 80
I mean,
again.
I grew up in Wisconsin. It was
There you
like we had like 8 months of winter where temperatures didn't get above 40.
go.
Spring was like 45. Summer was like 98. That's there's no in between.
Wow. All right, so today is probably going to be a bit of a short lecture. Really, mostly want to talk through a couple more examples about really connecting the gas phase equilibria that we talked about before our first exam and never really did a whole lot with, connecting that to the types of equilibrium reactions we've been working lately. And so my plan for today is to kind of talk about that, do a little bit with Excel, and then save next Tuesday for more Excel work, answering questions you guys have. If you've got some interesting problems for me, you can send them my way, or we can kind of chat about them in class. I do plan to post a homework assignment tonight that will include at least one involved Excel problem. My thinking is I'll give you a problem that I would never give you on an exam in terms of both the content and the scope that you can do in Excel much easier, give you some practice with Excel. Maybe that will be something like the time it takes to reach equilibrium, which I specifically told you we're not really going to deal with too much. Something like that, maybe I'll just save for the homework to use Excel and to see how that can provide a handy input in that regards. And so then Tuesday, I'll be ready to talk about some approaches to that effect. Hopefully, I'll have some other examples. And again, I welcome if you have a certain problem you like to see how I would approach it in Excel. I'm happy to spend a little bit of time for my lecture prep solving your problem in a sense, or doing looking at it with you, assuming that it's related somehow to our class, right? So with that in mind, then that leaves Thursday for exam review. So I'm going to post a homework tonight. I have not started making it, so it'll be a bit of a late night for me. And then Thursday we'll go over that, and that'll be exam review as well. So essentially, the second exam is going to be on these chemistry topics. We will probably make use of a little bit of the mass balance stuff we did in the first section, add that to the flavor of the chemistry, but mostly the second exam will focus on the sort of chemistry, chemical equilibrium principles we've been going over. Any questions or concerns about that? All right, so if not, then we'll get back to where we left off last time, which was ionic strength. I had you guys solve this problem. It's a little bit of a rush, so I wanted to go through the solution with you just to make sure that everybody was tracking and catch any issues that you had along the way. And we did this kind of the very end of the class last time. So we were talking about ionic strength because it is important for equilibrium reactions. If we have too high of an ionic strength that influences stuff, and you can no longer really treat the concentrations just as concentrations. You actually have to consider the activity. Like I said, we're not going to get into that, but I did want to introduce the concept of ionic strength. So ionic strength then was defined as kind of the sum of all the ionic species. It was 1/2 times the sum of the concentration of each ionic species in the solution times that species charge squared. So it was some measure of how much charge was in the solution. Okay, pretty simple formula, and here's the way it would look for this problem written out, and I gave you this part. So the ionic strength is 1/2 times the magnesium concentration times its charge squared plus the chloride concentration times its charge squared plus the sodium concentration times its charge squared. So really this problem was just some calculations of each of these concentrations, and the real only tricky part would be that if you weren't remembering what to do with two different salts added to the solution, right? We had NaCl and magnesium chloride. So just want to double check that we're all tracking on the same page here. So essentially what we have here is chloride in both sets, and that was probably the only mistake that was made, if people made a mistake, is that you may have used the chloride from one of them, but not both in calculating your total chloride that would go there. Both are in solution, so both are contributing. I'm not sure that's the mistake. Maybe there's something else that maybe you just guessed or something, you didn't have the time. Feel free to let me know if you recall, but I'm just going to go ahead and work this out for you real quick. So from the 50 milligrams per liter of magnesium chloride, we can take this and convert it to moles per liter. That's what we're going to need to do. So we'll multiply this by 1 gram per 1,000 milligrams. So divide by 1,000. And then we can take that and divide it by our molecular weight for magnesium chloride, which would be, if we say magnesium chloride, that's going to be 2 chlorides and a magnesium. I'm just going to grab it. We'll go ahead and do this in Excel real quick. So the molecular weight there, let's say molecular weight, mg. That's 2 times the 34.45 plus the 24.3. So that many grams per mole for the magnesium chloride, 93.2. And we're going to need that to understand how many moles of magnesium chloride did we add in the first place when we added that 50 milligrams. We'll also need sodium chloride. That one maybe I can do in my head here, so that's 55.45. Okay, so then we're going to multiply this then by 1 mole MgCl2 per 93.2 liters. Excuse me, not liters, grams of MgCl2. So that's just dividing by the molecular weight. And when we solve that, that should give us the amount of moles of magnesium per liter. And that's also giving us some amount of chloride added to the solution as well. So let's go ahead and just say here, let me move this a little bit. So the amount of MgCl2 we added total was 50 divided by 1,000 divided by that guy. So that's moles per liter. Okay, so then with that, we know that we have 1 mole Mg2 plus per 1 mole MgCl2, and likewise we have 2 moles of Cl minus per 1 mole there, so 2 moles Cl minus. Okay, so if you missed that part, that would obviously change your answer as well. So that means that our magnesium concentration is equal to that answer, which I didn't write down. That was 5.36 times 10 to the minus 4. Counted the zeros right in a hurry. Yep. That means our magnesium is exactly that, 5.36 times 10 to the minus 4 moles per liter. And we could write our chloride concentration down based on that addition, but I'm going to wait a moment, right? So we have another form of another source of chloride, so I want to make sure to add that here. So I'm going to I'll go ahead and write that actually. So the chloride is going to be equal to 2 times that. But that's the chloride, excuse me, that's -4, not 14. That's just the chloride from the MgCl2. So I'm putting that little caveat here. And what I'll do is I'll just go ahead and write with a different color to track the sodium chloride, and then we'll add those two together. So then sodium chloride added is going to be that 50 milligrams per liter again. Do the same conversion. Again, multiply this by 1 mole sodium chloride divided by our 55.45 grams. So 50 times 0.001, that's just dividing by 1,000, and divide that by 55.45. So that gives us 9.02 times 10 to the -4th. And this is going to be the same thing as the sodium added. And this is going to add that amount of chloride, but that's not, again, that's not the total chloride in the system. That's just the Cl added from NaCl. So then that means we need to just put all of those together, and for the actual chloride concentration that we're going to fill in there, we'll say, I'll just bring it up to here, Cl minus is going to be equal to those two together, right? That 9.02 times 10 to the -4th plus this guy here, which was, we said, 2 times the 5.36. Didn't even write it out, sorry. 5.36 times 10 to the -4th. And that sum there gives us our chloride, and then we put in those numbers. So if you missed that step, or if you forgot to use the 2 moles there for the chloride in the magnesium chloride, then you would get the wrong answer. So we'll just run that through with Excel real quick, just to kind of prove to ourselves that all that is good. So first of all, let's say that's also equal to the Mg2 plus. By the way, if you ever want to write an equation in Excel without it actually calculating the equation, because usually if you press equals and then stuff, it's going to treat it as an equation that it needs to solve. You can put an apostrophe in front of it, and then it's just going to leave it as text. So that's what I just did here. And then you see it's not giving me any errors. It's just like, oh, okay, this is just text. So if you ever needed to do that, that's the way to do it. So this is going to be equal to the Na plus there. So then the chloride, Cl minus, is going to be equal to this guy plus 2 times that one. Okay, so that should be then our 3 different concentrations that we need. That means our ionic strength is going to be equal to 1/2, so 0.5 times, we have the magnesium times 4. I just went ahead and did the 2 squared in my head, plus our sodium, oops, didn't mean to go out of the system there, sorry. I don't know why it's doing that. Okay, let's just cancel that. Okay, let's try again. 0.5 times magnesium times 4 plus our sodium times 1, so just leave that alone, plus our chloride concentration times 1. It's a negative 1 squared, so still 1. And then that should be our ionic strength. And technically this is kind of moles per liter. This is sort of a moles charge, or moles of effective charge, something like that, per liter. So maybe it's correct to call that M. Maybe some debate about that. Okay, so that gives us our final answer of 0.0025. Okay, and I don't remember what exactly the quiz provided as answers, but I think what I did was I took kind of a few of these answers in case you got partway confused there. There's potential wrong answers there. All right, any questions on that? We good? All right. So just a quick recall here about Henry's law. Got a couple of quick little problems for you to solve. Just remember here that Henry's law essentially is, we're saying that we have a concentration of something, let's say in this case oxygen, is going to be equal to the pressure of oxygen times some constant. So K, Henry's constant for oxygen. So there's a couple of things here. We've got CO2 and oxygen at different temperatures, and this is in moles per liter times atmospheres. I guess that's per liters per atmosphere. So we can use that to solve for the dissolved concentrations here. And so given that, what I'm asking you to do is give me two answers. First, the dissolved oxygen at 0 degrees Celsius, and then at 25 degrees Celsius. And I'm asking you to give that to me in milligrams per liter. And what you'll see here is there's a reasonable difference, which, you know, if you ever work with aquatic chemistry or aquatic ecology, one of the very important aspects, of course, for marine and aquatic life is how much dissolved oxygen is there, right? There's some fish species that will not live in certain areas because there's not enough oxygen. Sometimes that's just simply temperature dependent. So go ahead and take a look. And at 0 degrees Celsius, really, we're still talking liquid water, not ice. Okay, and then the last thing that I probably should have reminded you or told you to assume is that about 22% of our atmosphere is oxygen, right? That would be probably the missing piece here. So and we're at 1 atmosphere. O2 there. Yeah, so that subscript that I wrote there was K with a subscript H, comma O2.
true that colder water holds oxygen better than warm water?
Yes.
Oh, then my calculation isn't making sense.
That is the part of the point of this exercise. We should see that the colder water is going to have a higher concentration of dissolved oxygen. Yeah. So if that didn't work out for you, take a moment to see if you can find the spot there. And that is why you won't find trout in Louisianan rivers unless they're maybe stocked in the northern rivers or something. But even then, because they need more oxygen. Yep. Okay. All right. So let's take a look together. See if we can make some sense of this. R value? What do you mean?
Isn't, like, do we use TB? Was that our T for this one?
So technically you've got the partial pressure of oxygen already. So I think you don't need it. Okay. Although, as I'm saying that, I'm thinking to myself, well, how are we getting per liter? So let me see if I can get there while talking, while writing it out with you. I grabbed this example from the book. I think actually, no. Okay. And it's not a particularly difficult problem, so we should be able to get it. So oxygen here, and I don't mean that you should have got it right off the bat or whatever. I just mean we should be able to figure this out. So the partial pressure, that's going to be 0.22 atmospheres, because we assume that there's 22% of the atmosphere is oxygen, and that we're at 1 atmosphere pressure. So that means the partial pressure is 0.22 atmospheres of oxygen. Multiply that by the K, which is in, it had liters right there. So yeah, there we go. You see the problem already?
What? Yeah, no, I plugged in the wrong K value.
Okay, well there you go. Yeah, because there's CO2 and oxygen here, so there's a couple ways you could go wrong here. So let's say we'll do 0 degrees Celsius first. So this would be times 0.0021812. This is in moles per liter per atmosphere, the units. So when we multiply that leaves us with moles per liter. So in this case, we didn't actually need the ideal gas law. So we didn't need R, we didn't need any of that, because we could assume we already know the fraction of the atmosphere that is oxygen. Okay, so let me grab Excel, pull it over. Okay, so if we take that K then written out here, and we say our oxygen is going to be 0.22 times that K, that gives us 0.0048 moles per liter, or that would be, I guess, 4.8 times 10 to the minus third. So 4.8 times 10 to the minus third moles per liter. Then, of course, we need it in milligrams per liter, which is a lot of times what we're measuring in if you're ever doing any field sampling. So we'll convert that. So we'll take 4.8 times 10 to the minus third. Yeah. Missing a 0 in the K. You're exactly right. Thank you. So missing a 0 here. Great. Thank you. All right, great. So then 4.8 times 10 to the minus fourth actually looks a little bit more appropriate anyway. So we'll take that moles per liter, and then we can multiply that by our oxygen is 16 grams per mole for 1 oxygen atom. So that's 32 grams per mole for the O2 molecule. So 32 grams per mole. then of course we're going to want to convert that back to milligrams instead of just grams. So we'll multiply by 1,000 milligrams per gram, and that should give us our final form of milligrams per liter. So we need to take this times 32 times 1,000. That gives us 15.35 milligrams per liter. That's for the 0 degrees Celsius one. So 15.4 milligrams per liter. All right, does that make sense? Great. So then, just based on my experience, have a little bit of fieldwork experience and measurement experience and stuff, I expect that the 25, just as a guess, to be at most about 10. So between 8 and 10 is a typical, if you go out in the field and measure something, if it's a particularly hot day in Louisiana and it's muddy, like muddy water with lots of junk in it or lots of organic matter, probably a lot less than 8 to 10 range, right? But if you're to take, maybe go to the Comeet River and dip a oxygen probe in during summer, I'm going to guess it's somewhere around 8. So I'm going to guess the 25 degrees Celsius probably between 8 and 10. So let's check it out. It looks like I got the right number of zeros that time. Stop. And I'm just going to copy that same process, and I think it should just port over nicely. So 0.22 times the K, and then we have the same conversion from moles per liter to milligrams per liter. So when we do all that with the other K, we get 8.9 milligrams per liter. So at 25C, go ahead and be thorough and say 2.78 times 10 to the minus 4th moles per liter. Oops, that's probably third, isn't it? No, that's fourth. Okay. Or how is that a smaller number? What did I do? Oh, obviously it's a smaller number. I'm sorry. You can't tell me it's obvious, can you? You're having a brain fart. Okay, so anyway, 8.9 milligrams per liter. Okay, so there we go. We proved to ourselves that higher the temperature, the lower the oxygen, and presumably this trend continues downward, less oxygen the hotter you get. Trends like these, maybe they're always linear or always have that relationship, but some cases maybe there's some distinctions. Turns out some other co-solutes can change the solubility as well. Chloride, for instance, if you have a lot of chloride in your system, that may decrease this equilibrium constant a bit also. Okay, so that's kind of just a reminder about Henry's law, kind of refreshing your memory. And now I want to get into an example where we actually need both the gas to liquid and an aqueous equilibrium. And that is, there are several examples. We mentioned chlorine last time in terms of you don't want it to accidentally degas, drive off chlorine gas while you're doing anything cleaning wise or disinfecting. But ammonia, we can actually use ammonia's gas form, NH3, is a gas. You can also dissolve it, so you've got dissolved gas, NH3, and I just wrote aqueous here. Just like oxygen, right? You can dissolve oxygen and it's O2 in the water. So we have that equilibrium in terms of the gas to liquid phase governed by a Henry's law constant with the value given here. And then once ammonia is in the water, then it's in equilibrium with the ammonium ion. So NH4 being ammonium, and NH3 being ammonia, right? So IUM for ion, ammonium ion, and this would be ammonia. And in equilibrium like that, it can react with a proton, a hydrogen, and form that ammonium ion, NH4 plus, or go backwards. So we have this reaction here. Another way to consider it would be to take the ammonium ion and react that with a hydroxide ion, and that's going to form back to ammonia and a water. Okay, so there's a couple of different equilibrium reactions at play here that can be important for the system. And so when we're dealing with ammonia and water, both factors are happening here, and you're going to have some ammonia in air as gas. So if you're ever cleaning with it, you want to be cautious to have kind of an open ventilated area so you're not just breathing in all that ammonia gas all the time. And then guess what? This chemistry is happening in your lungs too now, because there's aqueous media in your lungs, there's in the cells or just around. So you don't want that. You don't want a lot of that. It's going to be an irritant. And so there's a few considerations to make. If you can keep it all as NH4 plus, ionic species can't really volatilize into the air. You can't have ionic species as ions in air because there's no solvent to provide a counter ion. Then you have a charge imbalance. That's just not very possible. Or maybe you can if you have a plasma, something like that. Anyhow, both of these things are going to happen, and we can make use of this action, and we can manipulate this action intentionally to do what we would call ammonia stripping. So if we've got a lot of ammonia in a wastewater, which is a common byproduct of decomposition of organic matter, so if we're decomposing organic matter by some biological process, get a lot of ammonia. Or perhaps we have an industrial process that's producing a lot of ammonia. We have then a lot of ammonia in a waste stream, and we want to get it out. So then what can we do? We can blow air across the water, literally just kind of create either a chamber where it's like a shower with air blowing upwards, water pouring downwards, and you strip the ammonia out of the water. Or in some cases, maybe we use the principle in reverse, and we're taking some gas or some particulate matter out of the air and clean the air and get it into water if that's an easier way to treat it. So depending on the situation, air stripping is typically taking ammonia out of the water, but the same type of process can be used in reverse by using these principles. Ammonia in particular also has the equilibrium chemistry reactions in play. So we have an example problem I wanted to go through, and we'll fiddle around with Excel for a little bit with this and give you a few minutes to take a look at it. So nitrogen in a wastewater treatment plant is in the form of ammonia and ammonium ion and has a total concentration of 7.1 times 10 to the minus 4th moles per liter. So it gave us a lot of information already. There's a total. I mentioned sometime recently that the total concentration is an important parameter. We can actually even go ahead and write that is NH3. Yeah, we do that. So that's NH3 plus the NH4 plus is equal to that amount, that 7.1 times 10 to the minus 4th moles per liter. So right off the bat, we're given that. So two unknowns there, but that if we have a system of equations, that may be a part of it. Okay, Henry's law constant is given at 57 moles per liter per atmosphere, and part A says find the fraction of nitrogen that is in the ammonia form and hence strippable as a function of pH, and draw a graph. So find an equation that's describing the, so I guess I said find, derive an equation that gives the fraction of the nitrogen. It says nitrogen. We're assuming that the only nitrogen species here is either ammonia or ammonium. So the fraction of the nitrogen that is in the ammonia form, so that's the fraction of the total, as a function of pH. And then if you've got a calculator, maybe use a few pH points to plot a little graph. So just to get you started here, that's essentially going to be that NH3 concentration over the total concentration in some form of an equation that has the hydrogen concentration. let's work towards this. So I put here the NH3 divided by total. That needs to be some function of our H plus, because that'll be our pH function. I'll go ahead and write in, rather than write in the numerical total, what I'm going to do is write in NH3 plus NH4 here, because I think we might be able to simplify before using that. We're still going to use this equation up here, but it may make sense to manipulate this without that first. Okay, so that's the equation that we're looking for is going to be in that form. What we have is one here, and then another equation saying that our Ka for the reaction is going to be equal to, and if we remember a moment ago, we were looking at these reactions, and we have this one here, NH4 plus and NH3 and H plus. And that's the one we have the pKa for. I should have been a little more clear for that, but that's this guy. And so what we can say then is that's going to be equal to NH3 times H plus, divided by our NH4 plus. Okay, so that's one equation that we have, and we have this other equation with those two, and trying to solve or simplify into this form. That's kind of the target here, and we want this all as a function of pH, right? So we did a problem last time where there was a pretty quick simplification. I took the long way, and one of you guys pointed out the short way for the fraction. We'll see if which way is quicker this time. But if we divide the top and the bottom by NH3, this is going to be 1 over 1 plus the NH4 plus divided by NH3. So then that can be pretty handy if we convert this guy over here to Ka divided by H plus is equal to NH3 over NH4 plus. And what we'll recognize is we can just flip both sides of that, and then we have a matching set over here. So this NH4 plus over NH3, that's going to be the same as saying H plus concentration over Ka. So this is 1 over 1 plus that H plus over Ka. Okay, so that gives us a fraction of the total in terms of the pH, or the proton concentration, right? So without even dealing with the total amount there yet, we didn't really need it. We could get that fraction, and that actually makes sense, right? We didn't need the gas phase stuff for part A or the amount that was given for part A, because we were just looking at a fraction that's going to exist based on the pH. So that was really just a question dealing with the stuff we've gone over the last couple times. So if we do that in Excel, let's bring that over. We'll take a few different pH values as an example. Let's go ahead and write out we'll say our fraction equals 1 over 1 plus the H concentration divided by Ka. That's going to be kind of the form we use for this. And if we take an arbitrary set of pHs, you can kind of pick whatever you want. We should be able to use Excel just to calculate, based on that, what our fraction is. So we'll say the fraction then is going to be 1 divided by 1 plus, and here we're going to call our pH. So what we're going to do is 10 to the minus pH, and take that divided by our Ka, which I had written down here. And that should be our fraction. So the fraction of total, really this is the fraction of NH3, right? And in acidic conditions, we expect it to be not a whole lot, because let's see, did I say that correct? Is that correct? I think that sounds backwards. So let's just fill this down and see what it looks like. Looks like a mess. So what did I do wrong here? Oh, well, first of all, that B16 was filling down, so that's obviously a mess. Okay. So the fraction that is NH3, yeah, that's right. Okay, so at low pHs, NH3 could take another proton. So if at low pHs, it's very likely to take another proton and be all NH4+. Okay, so I was just like doubting myself there. So if we take a look just visually, we see that, we going from like 1/1000th of the stuff in solution or 5 billionths, I guess, is NH3, down to, if we are at pH 8, then 5% of it is NH3. pH 9, 35%. And then it jumps because we just crossed the pKa, and now we're up at 84%, up close to 1, up at pH 12. So then we want to graph that. Go ahead and make this full screen here. So we'll plot it, and as usual, I would suggest, this time I guess we could maybe use a graph that'll sort of fill in the blanks for us a little bit in terms of the lines. There are certainly ways you can just you can select your data beforehand and plot. A lot of times I like to just add it series by series. That's totally kind of up to you. Okay, so what I did here then was I plotted it as the pH value versus this fraction, so we can see that. And technically we could extend this down a couple to pH 14. See if that, yeah. There we go. And then we could adjust the graph to continue with that. But what we'll see is it's basically asymptotic near 1, right? One thing to consider here is that on the x-axis, this is the pH. That is a log plot. On the y-axis, this is not a log plot, although potentially we could make it a log plot if we wanted. And you'll see some log plots like that, especially if we have multiple species and we want to see that some of them are like 10 to the minus 4th or whatever, to really get a good feel for how far low of a fraction this is. Because right now we just know that it's less than 0.2, right? But if we put this on a log plot, then let's just tell Excel to do that. We'll put it on a log scale, base 10. See something very different. It kind of tells the same story in a way. Another thing we could do is, instead of just doing a log plot, we could take the log of those fractions, because that'll give us log of 0.01 is like 10 to the minus 2, right? So that's a minus 2 there. And we can plot it as if we were doing like a microbial data or something, like how many logs reduced are we? So we could plot it that way, manipulate the data, instead of just leaving it as a fraction, say equals the log of this. Move the graph out of the way. And then plot that, so it'd be the log of the fraction, and it comes very close to zero when we're nearing 100% of our solution. Different ways you can look at it. You'll see some plots in either direction. I guess for now the plot where we had it might make a little more sense. So see about putting that back. I want the axis, please. That was it. So we'll put it back. There we go. Okay. So any questions, issues, curiosities with all that? Kind of makes sense? All right. So let's take a look at part B then. So same problem, and then part B asks if the wastewater pH was raised to 10 and the atmospheric ammonia concentration is 5 times 10 to the minus 10th atmospheres, what would be the equilibrium concentration of total nitrogen in the wastewater after air stripping? Okay, so we've done the process. A lot of that ammonia has gone into the air, and we have measured that amount of ammonia in the air. Now we're wanting to know what the concentration in the water is of total ammonia or total nitrogen after air stripping. I'm going to move the Excel sheet out of the way. Okay, so this time we're going to be using that principle of Henry's law, where we have a relationship between the concentration of the stuff equivalent to the Henry's law constant times that partial pressure. We're given that partial pressure was measured here. So we should be able to know how much ammonia is there, and then from that, determine the total ammonia given the pH, right? So that's going to be the process here.
actually? Or
Yeah.
okay.
If we take a look at the Excel or the work that we did in part A, then our fraction um, of nitrogen that is in ammonia form is 0.85. So 0.85 of the total is NH3. Here's one way you could write that we could put into our system. Okay, so this, with that, what I said, it turns out to be pretty simple from there. Again, we didn't actually need the total concentration that was given to us. Never really ended up using it, so that was pretty much a red herring in the problem. But based on the Henry's law constant, the 57, times that 5 times 10 to the minus 10th atmospheres, that gives us 2.85 times 10 to the minus 8 moles per liter right here. I'll go ahead and show you that that's just what I entered in here. So I'll write that in, 2.85 times 10 to the minus 8. That'll be moles per liter. And based on the fact that we know that we have some fraction, and by the way, I guess one thing you could check, if you really wanted to consider if the problem was like hiding some information from you, or if you just checking that, make sure you didn't do something wrong, this number should definitely not be more than what we knew was in the stuff to begin with. So we can just double check that that is a smaller number, and yes, it certainly is. Presumably, it has to be a smaller number because we've taken some ammonia from the water out. So a good, decent way to double check what you're doing is in the right direction at least. So that's the moles per liter of NH3. That means we can take that and say, well, the total is just going to be that divided by 0.85. So the total then, and I just did that in Excel real quick, is 3.35 times 10 to the minus 8. Okay, so then that would be our answer. Any questions? Does that make sense? All right, so I'll make sure to give you some good practice homeworks. Solutions here, I guess maybe it asked for the percentage removal as well. which I forgot to answer. But that percent removed is going to be 1 minus what's remaining. There's very little remaining. So that's where I guess we did use that total amount that was in there. So finally, it's relevant if I had read the problem correctly. What would be the equilibrium concentration? I guess I did read the problem right. But then they just went one step further to see, okay, how much of what percent or how efficient was it to answer that. Okay, so that's pretty much all I have for you today. We'll do a quick Kahoot and get you on the way. I had it up. Anyone else need a moment to get in? All right. I'll see you guys on Tuesday. Remember to let me know if you've got something in Excel that you want to go over in particular. Could be a concept or anything.